So where are we in the VQE thing? So let me just go to I'll just open YouTube. I'll go to the playlists, and I'm just looking for where I left this, because in the past weeks I've been sort of working. I kind of went back to the very first algorithms, and I spent some time diving in there, and then now I wanted to kind of close and try to close the VQA playlist. And I was like, I think I just wanted to kind of quickly catch up where I've been.
I've been putting this topic aside for a while now, and I kind of have a hard time coming back to it. But I really wanted to get a bit deeper into the variational quantum.
So first, it seems like first I went through these basics, and then I remember that here I had trouble understanding what the expectation value is, which I understood then later on, thanks to a couple of other things, that this is basically the average measured value, so to say. Good. So, but I think this is all that I took from this.
I guess
Concept of the ansatz and all this kind of stuff.
That you start with, the more likely your VQE will perform well, as you correctly said in your
question. Okay, so the next video.
Just use any knowledge you have.
The next video is why would phase estimation give me also? Can I just switch to? Can I just switch to black, to the black design here, to the dark theme? I like it more. So why would phase estimation give me also an answer to minima? Okay, so yeah, because this is something that was in David Kopchik's. So this is me literally trying to recap where I left. So this is gonna take a little bit, sort of the first part of this video. Probably if you wanna just keep that, but I don't know exactly how long it's gonna take me. It's just I remember now in hindsight, I kind of I think understand why would you be able to use quantum phase estimation as is to get that right, because at the end of the day, if you've got an ansatz, if you've got a circuit that represents your Hamiltonian, right, which is basically the energy operator of your particle that you're studying, right, and then which basically defines how the energy evolves. The lowest energy values are those energy values that basically are not moving, right? So they are not like, so so this translates into those values being actual eigenvalues of that Hamiltonian, because remember then I did another video later on eigenvalues and eigenvectors, which is I think even a bit more confusing, but now it's all a bit more clear thanks to the course from Rod, the course from Future Learn, because they basically put it in a really simple way where it's like, yeah, well, those are, so the eigenvectors and the eigenvalues are basically those which do not move, or they're not affected by that transformation, or by that operation. So that's why the lowest energy levels are related to the eigenvalues and eigenvectors. And if you then connect that to the way, I don't know if I can find it here, just give me a second. So Amazon, no, the Kindle thing, Kindle Cloud Reader, because I think I got it there, but I don't know if I have to sign up to log in here. It's gonna remember my credentials, probably, yes. Because I got a bunch of stuff in here, and this in here. So this is the O'Reilly book, and then when you go to phase estimation, they actually put it like that also. So phase estimation. So basically, what it's saying, the way they put it, which is also then useful to understand the whole thing, is that the phase estimation helps you find the eigenphase of an operator, right? And it's funny because I think it's it's so far the only learning resource where I've been able, where I've seen this explained like that, right? And they explain here the case of the Hadamard, and they say um, basically the Hadamard has some eigenstates that if you apply them, there's no um, observable change. I mean, there's a change here in global phase, but there's no observable change. And so this is and then basically the idea here is, what am I doing? Um, so that register here is where you put your sorry, this is the operation you want to find the eigenphase from is here, right? And you apply it conditionally. So I think there's even an example. Yeah. So that's roughly the concept. And you see that it stays unchanged, right? And then but then that eigenphase is really I don't know if I can say that really is transfer via phase kickback, because it's not that you get the eigenphase in here, but then you kind of got to make like a bit of an extra calculation. Yeah, but it's basically this. So again, this is one of those things where just connecting a bunch of dots here and there, and so this now makes more sense. Now, phase estimation is expensive, right? Because you know you got to use a lot. You got to use a lot of qubits to actually run that in a sort of at a meaningful scale. So what VQE is doing is trying to approach that from a different perspective, where you prepare. So you're basically preparing an ansatz, like a circuit, and instead of applying, so that's supposed to represent your Hamiltonian, right? I understand. And then instead of applying the QPE, the QPE, you basically uh, get an expectation value, right? So you measure it you measure it several times, and then you get the average, and then there's sort of a classical part of the algorithm that tries to find, so it helps you sort of with gradient descent or something like that. It helps you then find another set of parameters for your ansatz so that expectation value is minimized. So that's what you're trying to do basically. Okay, yeah, I think that basically makes sense. So
it describes how does the energy of the system evolve.
So I think that's
second quantization, whatever that is.
I don't even remember.
I'm really just reading. I don't understand most of the stuff.
Doing here, checking the paper, and then I went through. I think I was a bit lost in here, and then I went through. I started going through. And then by repeated measurements, estimating. I was going through a circ tutorial that basically helps you implement sort of the variational quantum algorithms, and that's exactly what it. And there's a VQE example. Class of algorithms known as variational quantum algorithms. Indeed, this approach is not just limited to finding low energy eigenstates, but minimizing any objective. Exactly. And that's what I wanna, where I wanna pick up today. I mean, I don't know how much I'll be able to do today, but basically represents that. But basically, I will try to. I say basically a lot, but basically I'll try to, that's kind of my next focus, is to close this and then close QAOA, and close the Yellow Submarine project. I don't know if you remember that. It's a project that I started reproducing some months ago, actually. I just didn't know how much of a complication I would get into with this whole continuous quantum computing stuff.
So destination integer values may have a non-integer mean. It is a fundamental concept in all areas of quantum physics.
Terminology is important. As an example, expectation values is such a. It looks like such a normal, innocent term that it was. I got so confused.
How do we the beat, right? Because basically, if you open Quirk, I can quickly show that what it kind of all clicked together with also what Craig was mentioning when I asked about the it's not that it gives you that energy, is that it gives you the eigen it gives you the eigenstate, it gives you the eigenphase or the eigenvalue, so that you can calculate the energy using that. Okay, I think that is the way.
I don't know. I don't know if this is it, man.
I think this is it. This must be it.
Okay, let's try to find what's the URL for that. Circ read the docs. Okay. Just basically, where did I? Because I've got here the Jupyter notebook I just started, and I was like taking a look at what I did. Basically, probably just copy pasting that stuff. Um, Good one. Create a circuit on a grid. So I was basically going through and understanding sort of the way circ works. And that's a circuit I ended up having. That's where I left last time. Exactly. Uh, but again, I don't remember how did they come up with that particular ansatz. There's a lot of freedom defining a variational ansatz. Here we'll do a variation on a QAI strategy and define an ansatz related to the problem we're trying to solve. Exactly. Because the QAI strategy is there's an example with the 3-cut problem where you're defining a circuit, an ansatz that is basically sort of a mapping of the problem. Okay, I mean, this is just me going through eigenvalues and eigenvectors. I don't even know why I even dived into trotterization, but then creating an ansatz. And this is where I started really, getting into that. Yeah. Okay, cool. Good recap, I think. Those videos are definitely useful, just for me at least. Good. Let me close that. So let me just quickly read through this, creating the ansatz. So this is like the basics of circ in here. I might want to recap that as well. The grid qubits. It's like, does it have to be a grid? But I think this has to do after. Now again, it's again connecting dots, right? So after going through the course from FutureLearn, I kind of understand that. So the concept of having this thing in here makes sense because it's directly, I think, it's the way you lay out the qubits, right? So if in your chip the qubits are in a grid, then that is relevant, right? Right now, it's relevant because you need to be able to identify which qubits you're talking about. And so, if you imagine you have them on a grid, that also defines which qubits can interact with each other. And I think that's the reason why this is in here. Cool. Yeah. So, because I was a bit confused, because like, why would you define them in a grid, and if this is just um, a bunch of them together? But now I realize that that's probably what makes sense. That's probably the reason. Creating the ansatz. Yeah, I actually pretty much like the idea of the of sub circuits. This last case yields a nice pattern for defining some circuits layers. Parameters. So these half turns, rotation gate. Not now. Later. I'll update later. Another important concept here is that the rotation gate is specified in half turns. So rotation about x, this is the gate. Um, okay, so one half. Yeah, okay, so one half turns. One half turn equals to then just 1 times pi. So pi. Um, okay, so first, so this is where I wanted to. No, I mean there are two things we can do. One thing is that try to understand how the problem is represented, and then or just go all the way to the end, because I basically copy pasted all that stuff and I created that circuit, which is obviously a little bit different than theirs, because uh, there's a bit of random stuff in here, as far as I remember well. As far as I remember, and so you've got the circuit in here. Um, can I just can I? Is there a way to run everything? Run, 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 run. So you've got the circuit now here. Um, and now simulation. So let's go through. Let's do the following. Let's just go through all the way. Through the end. No. I'm feeling a bit more like, let's try to understand the circuit. Let's do this then. So um, let's go back here. First, we need to choose how the instances of the problem are represented. These are values j and h in the Hamiltonian definition. We will represent these as two-dimensional arrays, lists of lists. For j, we will use two such lists, one for the row links and one for the column links. Okay, so but first, let's open up this here. No. Oh, come on, that's just a QAI paper. I forgot about this. Okay, but what was the problem actually? What was the example? Um, Something, it was a chemistry thing, but I don't remember. Oh yeah, this one here. The classical problem we'll focus on is the two-dimensional plus minus Ising model with transverse field Ising. This problem is NP complete, so it's highly unlikely. Okay, the two-dimensional plus minus Ising model with transverse field. So this is the problem we're focusing on. Ising spin glass models. In the spin glass with Ising spins, the problems of computing the magnetic partition function and finding a ground state are studied. In a finite two-dimensional lattice, these problems can be solved by algorithms that require a number of steps modeled by a polynomial function. In contrast, this find the same problems are shown to belong to the class NP hard problems, both in the two-dimensional case with a magnetic field and in the three-dimensional case. NP hardness of a problem suggests that it is very unlikely that a polynomial algorithm could exist to solve it. Magnetic partition function and finding a ground state are studied. Okay. Ising spin. So this is a QAOA paper. So but what is really, and you need to understand the problem first. The Ising, okay, so the Ising model. The Ising model, named after the physicist Ernst Ising, is a mathematical model of ferromagnetism. Okay, in statistical mechanics, the model consists of discrete variables that represent magnetic dipole moments of atomic spins that can be in one or two states, +1 or -1. Okay. Um, the spins are arranged in a graph, usually a lattice, allowing each spin to interact with its neighbors. Uh, the model allows the identification of phase transitions as a simplified model of reality. The two-dimensional square lattice Ising model is one. Okay, the two-dimensional, this is exactly what we're focusing on. The two-dimensional square lattice Ising model is one of the simplest statistical models to show a phase transition. The Ising model was invented by physicist Wilhelm Lenz, who gave it as a problem to his student Ernst Ising. The one-dimensional Ising model has no phase transition and was solved by Ising in 1925 himself in his 1924 thesis. The two-dimensional square lattice Ising model is much harder and was given an analytic description much later by Lars Dalal. It is usually solved by a transfer matrix method, although there exist different approaches more related to quantum field theory. Okay, so this is an actual model um, of ferromagnetism. Okay, so this is okay, and this model basically describes what does it describe? Basically, the spins are arranged in a graph, usually lattice. Okay, statistical mechanics. Definition. Discussion. So here you've got all the, okay, this is the J and the H that the Google paper is talking about. Okay. Okay, so a significant number of a significant number of statistical questions to ask about this model are in the limit of large numbers of spins. In a typical configuration, are most of the spins +1 or -1, or are they split equally? Basic properties and historical significance. Can I describe a phase transition based on the following argument? The petition. Okay. Function. Pearls drop. Pearls droplets. That's super interesting, though. Monte Carlo methods for numerical simulation. Quench of an Ising system on a two-dimensional square lattice. Definitions. The Ising model can often be difficult to evaluate numerically if there are many states in the system. Consider an Ising model with L, the total number of sites in the lattice, individual spin site in the lattice, state of the system. Since every spin has ±1 spin, there are 2 to the power of L different states that are possible. This motivates the reason for the Ising model to be simulated using Monte Carlo methods. The Hamiltonian that is commonly used to represent the energy of the model. Here you go. I hope I'm recording. So here you've got the Hamiltonian that is commonly used to represent the energy of the model. Okay. Furthermore, the Hamiltonian is further simplified by assuming zero external field. Okay, so okay. Given this Hamiltonian, quantities of interest such as the specific heat or the magnetization of the magnet at a given temperature can be calculated. Okay. Exact solution. One-dimensional two-dimensional solution with transverse field, 2 dimensions, transfer matrix. That seems, I think that's kind of one of the other methods more classical method. Okay, spin flip creation. Oh, there's even more dimensions. Okay, so but basically what this whole thing is a model, uh is a model for ferromagnetism. The mechanism materials form permanent magnets, okay, or attracting magnets. It uses several different types of magnetism, okay. It's the strongest type and the response for the common phenomenon of magnetism in magnets, okay. So it's a model for magnetism. The model consists of discrete variables that represent magnetic dipole moments of atomic spins that can be in one or two states. Okay, so it's arranged in a graph, usually a lattice, and the model allows each spin to interact with its neighbors only. The model allows the identification of phase transitions. What are phase transitions in this case? The term phase transition or phase change is almost commonly used to describe transitions between solid liquid. Okay. As well as plasma. Okay. As a simpler model of reality, the two-dimensional square lattice Ising model is one of the simplest statistical models to show a phase transition. Square lattice Ising model. In statistical mechanics, the two-dimensional square lattice Ising model is a simple model of interacting magnetic spins. The model is notable for having non-trivial interactions, yet having an analytical solution. The model was solved by Lars Onzaga for the special case that the external magnetic field is zero. An analytical solution for the general case has yet to be found. Critical temperature. Okay, so that's the lattice, and those are the spins. Okay, so those are these plus ones and minus ones on a dual lattice. Exact solution. Spontaneous magnetization is boom. Yeah, but what is the solution? Like, I mean, it's a model, so you can ask it questions, I guess, and basically about the interactions and the ferromagnetism stuff. Okay, but that's a good start, I think. What was this J's and H's discussion? The minus sign on each term of the Hamiltonian function is conventional. Using the sign convention, the Ising models can be classified according to the sign of the interaction. If for all pairs I and J, J is bigger than zero, the interaction is called ferromagnetic. If it's lower than zero, it's called antiferromagnetic. And if it's zero, it means non-interacting. Otherwise, the system is called non-ferromagnetic. In a ferromagnetic Ising model, spins desire to be aligned. The configurations in which adjacent spins are of the same sign have higher probability. In the antimagnetic field model, and adjacent spins tend to have opposite signs. The sign convention of H also explains how a spin side J interacts with the external field. Okay. Namely, the spin side has to line up with the external field. Okay. So I think basically what this is doing is they're just creating a random model. So the classical problem will focus on the two-dimensional Ising model with transverse field. This problem is NP complete, so it is highly unlikely that quantum computers will be able to efficiently solve it across all instances. Yet this type of problem is illustrative of the general class of problems the circuit is designed to tackle. Consider the energy function. Okay, so that's the Hamiltonian we saw in the Wikipedia. Yeah. what was that? That's this one here. Yeah. Uh, yeah. Kind of. Where each S I J A I J and H I are either plus one or minus one. Here, each index is associated with a bit on a square lattice exactly, and the IJ notation means um, sums over neighboring bits on this lattice. Uh, the problem we would like to solve is given given Ji, Y, and Hi, find an assignment of Si values and minimize E. Um, so the parameters are the S things here. But why is it that you're given a J? And H, what was that? The J and H. So okay, so H is the external field. So furthermore, the Hamiltonian is further simplified by assuming zero external field. Okay, so the H is the external field. And what is J? The energy of the model using Monte Carlo method is, okay. What is this J then? It's explained in here. So these are the S's in our the minus sign on each term of the Hamiltonian function is conventional. So that's the interaction, okay, for all pairs IJ. Ferromagnetic. So those are the plus. Okay, so okay, so these are the actual pluses, plus and minus ones, and the external field, I guess, is the same. It's going to be a plus or minus one. How the spin side J interacts with the external field. Okay, so basically those are the elements of the lattice um, and this is the way it interacts with the external field, whether it's ferromagnetic or anti-ferromagnetic, so like positive direction or negative direction, exactly, sorry, or even no influence. Okay, so zero is also possible. And this is how they interact with each other, like the pair I and J. Okay, whether it's a ferromagnetic interaction or an antiferromagnetic. Okay, it takes time, but I mean, it pays off to understand what you're trying to solve. So basically, what this is saying is, but still, what are these S's thing? It's what you're trying to solve for, but what do they represent? Is it the state or what is it? The configuration probability is the probability that the system is in a state with configuration. This. No, those are the plus and minuses. Ah. For each lattice, oh, I think I know. I know. So consider the set of lattice sides, each with a set of adjacent sides, forming a d-dimensional lattice for each lattice k. There's a discrete variable such that representing The side spin. Okay. So that's the actual spin for any two adjacent sides. There's interaction, and also, okay, so the problem, so basically what we're trying to do is we're trying to say, okay, so you we are given um, what is the final interaction that what is the final interaction that we wanna get, right? Like for each of those different I don't know, they call it sides in here, but whatever. So for those are these different elements in for these different elements in the lattice, what's the final interaction you want? You want it ferromagnetic, you want it antiferromagnetic, or neutral? And what's also sort of then we're also given what's the and what's the desired interaction with the with external field. And so you have to and what we're trying to solve for is we're trying to find what is then the configuration of spins in that lattice that gives us exactly that exactly that in that result, that particular interaction between the different adjacent sides. I don't know if this is the right way to call it, but that makes sense. Oh, okay, good. Let's move on. um, da, 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 da. Here, each index I is associated with a bit on a square lattice, and I and j in addition means some. At least I already read. Sorry. Here. How does a variational quantum algorithm work for this? One approach is to consider n qubits and associate them with each of the bits in the classical problem. This maps the classical problem onto the quantum problem of minimizing the expectation value of the observable. Then one defines a set of parameterized quantum circuits where the gates or more general quantum operators are parameterized by some values. This produces an ansatz state. I mean, okay, but this we know. Okay, so this we know, like what's the ansatz and how is the whole concept in here, right? So I was just trying to understand the problem, but I think now I understand the problem. But now let's try to understand how it is mapped, right? So how is the ansatz created? Um, and that was later here. I don't know. Um, bum, 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 bum. Still have to. What's the actual difference between QAOA and a VQE? But I think it's in the overall, because VQE is basically doing this gradient thing, and QAOA it's not. QAOA is just a bit different. Or is also using, it's like what is which one is an actual algorithm and which this is still a bit confusing for me, and which is just a kind of or a way to construct algorithms. But here they call it just a strategy. So of defining an answer that's related to the problem. So okay, so how we do this? Good. Now I feel a bit better about this. So first we need to choose how the instances of the problem are represented. These are the values j and h are the Hamiltonian definition. We will represent these two-dimensional array. These as two-dimensional arrays, lists of lists. For j, we use two such lists, one for the row links and one for the column links. Okay. And so here's the code that we can use to generate the random problem instances. Rows and columns. Okay, so h and this length. Links within a row, links within a column. this I don't fully understand. Um, why a list of lists? How do you represent? These are values J and H are the Hamilton definition. We will represent this as two-dimensional arrays. For J, we'll use two such lists, one for the row links and one for the column links. Okay, so I get it that it's the lattice you're defining, so right? So it's a 3 by 3. In this case, the transverse field is this is the H. This is the H part of the of the Hamiltonian. So this is this H. Right. Not fully. How is this represented? Then apply an X power gate for the same parameter for all qubits. This method we have written above applies the Z power gate for the same parameter for all qubits where the transverse field term H is +1. CZ power gate for the same parameter between all qubits where the coupling field term J is +1 if the field is -1. Apply C by conjugated by X gates on all qubits. Okay, so this is already the next step, trying to understand why is this then laid out the way it is. But I still don't understand the problem representation. Why we're using two lists for J. Row J fields, column J fields. I mean, it's they all define a 3 by. No, this is 2 by 2 and 2 by 3, and this is a 3 by 2. Why are they represented this way? So you've got the lattice. Let me go back to the problem definition. Where each Si, Ji, J, and Hi are either -1 or +1. Here each index is associated with a bit on a square lattice. The IJ notation means sums over neighbor. sums over neighboring bits on this lattice. So da, 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 da. Okay, so still I don't really get why it's represented like these. Why lists of lists? I mean, okay, so I get it. It's a 3 by 3. It's a 3. So here in this case, it's a 3 is the length, right? So you're doing a lattice of 3 by 3. Now I understand the way the transverse to the H is defined. That makes sense. But then, what about the J? Why? Ow! Oh, sorry, I hit myself. Why row and column? Why row and column fields? I'm just stupid, I think. So maybe these are just the interactions. Row, but then links within a row. But why there are only 2 elements then? There are 3 rows and 3 columns, right? So rows and cols. Yeah, so here you can see it does length minus 1. Length minus 1. Column links. 0, 1, 0, okay. I don't get it. I don't get it why. Apply a Control Z power gate for the same parameter between all qubits where the coupling field term J is +1. So why? Given this definition of the problem instance, we can now introduce our instance will consist of one step of a circuit made up of. Okay, but this I'm just trying to figure out whether here there's something that gives me a clue why. So here you're iterating over Hij, rows and columns. So here conditioned on the JR and JC fields. JRIJ. So he's iterating over iterating over the why? don't understand why these have one, like length minus 1. It says interactions for J. We'll use two such lists, one of the row links and one of the column links. Why? Simplification. So H equals 0 for all J in the lattice. And plan becomes like this. When the external field is everywhere 0, the Ising model is symmetric using switching the value of the spin. Another common simplification is to assume that all the nearest neighbors, I and J, have the same interaction strength. Then we can set Jij equals J for all pairs Ij in the lattice. Then it's further simplified. Basic properties, historical significance, definitions for the Monte Carlo. Okay. Size of the lattice. J is then 1 to L. Standard system. Oh, so bad. Just specific here. This is the following energy equation. There's another way of specifying this problem. One dimension as exact solution. 2 dimensions. J1 and J2 are both negative. The Ising model becomes an antiferromagnetic. Blah blah blah. In the ferromagnetic case, there's a phase transition at low temperature. The problem approves positive magnetization for the nearest neighbor's case, and then so here we've got 2 fields. That's why it's called 2-dimensional, not so in 3-dimensional, it's not because it's a 2D lattice. Or is it? Just give me a second. So where am I? In the isotropic case, when the horizontal and vertical interaction energies are equal. Okay, so that's why we have JR and JC. So obtain the following analytic expression for the free energy of the Ising model as a function of temperature and horizon. So Onsager obtained the following analytical expression. So this thing in here for the free energy of the Ising model, and is blah 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 blah. And vertical interaction energies J1 and J2 respectively, horizontal and vertical. So this would be, okay, so you've got your sides in the lattice, right? I feel pity I don't have here a way to paint stuff. So you've got your things in a lattice, 3 by 3. So the role fields, this is the energy interactions between the rows, and because there are three rows, but basically there are 2 interactions between the row, I would say 0 and 1. And 1 0, I don't know. uh, then the column fields, this must have to do with this. I'll probably stop here right now because I'm running out of time, but I think for the session today, but I'll try to understand that a little bit more. But I think this is exactly why, because it's the 2-dimensional problem. So you've got 2 different interactions, the horizontal and the vertical. But I mean, that's part of the problem, right? Of how the problem is defined, I guess. Why though there's if the interaction energies are both negative, the Ising model. Why they have one dimensionless? No, this I don't understand. Why they have one length, like one? So this is the rows. So is it the interaction between the rows? Uh, Maybe we're assuming that there's some non interactions. I don't know. This is one of the things that I'm missing. I'll try to do a bit more research on that, but I'm happy with the progress I've done today. Catching up plus understanding the way the problem is, understanding the problem at all, the Ising model thing, and then basically understanding trying to understand how is it mapped to an instance of a problem, and then how are we going to translate that into an ansatz, and then the yeah, yeah. Still, how is this then parametrized, and how can it be possible that those parameters then belong to the actual, you know, turn into the actual evaluation of that Hamiltonian, right? That's what's interesting. Um, how the parameterization happens. So this is probably take at least a couple more videos. Want to finish understanding these, finish understanding how the problem is, mapped and how the answer is built, and then how is the parameterization alpha, beta, gamma, and how does this parameterization map to the Hamiltonian? And that's how this alpha, beta, gamma map to the actual finding the minimum. It's so simple. Yeah, no, there's a lot of overhead in me understanding the problem, right? So, but it's going slow. It definitely pays off. Perfect. Cool. Stay tuned for more.